Congratulations for making it in today. You've proven yourselves to be true Buffalonians. Is that the right word? Good. All right. All right. So today we're going to talk about one of the first kind of real steps into what databases can actually do. Now, before I actually get into the high-level meat of what we're going to talk about, before I get in, let me bump this up a little. Before I get into the meat of what we're actually going to talk about today, I want to get across a little bit of an experiment that I did a while back. Now, most of you are probably familiar with this book. It's the textbook for the course. What you may or may not know is that there are actually two versions of this textbook. One of them is what you probably have, and one of them is licensed only for distribution on the Indian subcontinent. Now, I bring this up for a couple of reasons. So first off, you're actually not supposed to know that that other book exists. Here's one particularly good reason for that. Okay, there we go. So here's one good reason why you're probably not supposed to know about this. And as far as you're all concerned, you don't know about this. But there's also a few other advantages to this small textbook. It is in paperback, so it's much lighter. It's much smaller, so it's easier to carry around. And, I don't know if any of you noticed me biking in. I bike a lot, especially in this weather. It's a lot of fun. But I have one copy of each of these, and you can imagine I usually want the lighter of the two to carry around. So this is super, super important for me. And yet a couple of years back, when I was first developing this course, what I actually ended up doing was carting around the heavy book. Back and forth, and I mean, why would I do that? Why does it make sense for me to cart around this big, expensive, super heavy copy of the textbook? Anyone want to venture a guess? Weight training, okay. Not that enthusiastic about my health. Yeah? That's... So this book has an amazing table of contents. It has an amazing index that has every single term that shows up in the book. The other book has a very, very short table of contents, just a brief summary of each chapter. It has only the most general terms in the index. And you know what? It ends up being completely useless for nearly everything that I want a textbook for. It takes me forever to find anything with this book. With this book, I can actually get through to what I want. Now, maybe this isn't a great justification for nearly 3 times the price, but to me it is. And in general, data is useful, but only if you can actually access it, only if it's organized in the right way. And so what we're going to be talking about today is data organization. How do you organize data in such a way that you can actually find it and make use of it? So getting back to all of this, one of the key things that we're going to be looking at is not just the organization of the data, but how that organizational structure interacts with the memory hierarchy. Remember, we want to keep our working set sizes as small as possible so that we can be as high up in the memory hierarchy as possible. Now, I kind of hinted at this a while back, 1 or 2 lectures ago, that there are kind of 3 different ways to organize your data. In a heap, in a clustered index, or in an unclustered index. And each of these provides one way to kind of structure your data so that it can be accessed. And today we're going to talk about the benefits and drawbacks of each method, we're going to talk about how these different methods interact with the lower levels of the memory hierarchy that they can be put on, and we're going to I'm going to try and give you a little bit of intuition about when each of these methods is, when each of these methods should be used. Now, the one kind of mantra for today is very simple. It's that I/O is bad, and all of our organizational efforts are going to mostly have to do with eliminating I/O operations. Now, it turns out that the kind of stuff that you do to eliminate I/O operations also speeds up regular query processing as well. But our kind of main focus right now is minimizing the amount of traffic up and down the memory hierarchy. All right, now I want to kind of use a little bit of a running example through today's talk. And before I get into that, or before I actually discuss how the running example pans out, I'd like you to do a little bit of thinking about the example yourselves. So here's a select query, simple select project join. And I want you to turn to your nearby neighbor and spend maybe, let's say, 5 to 10 minutes talking about how to, or coming up with a relational algebra expression for this query, and then thinking about both the maximum working set size and how much data is going to go through each of the operators if you put the operators in kind of a tree structure like we've been talking about. So take maybe 7 minutes. All right, where do I start? For the query, where do I start translating it? The data source. What's the data source here? I know you're tired trudging through the snow, but just a little more energy. Officer, thank you. All right, what's next? Rank, what do I do with rank? Selection? Okay. Selection, what's my condition? Rank greater than 3. Is that it? Rank greater than equal to 3. Am I done? No? And thank you. Good. Making, yeah. That's the level of energy I want. All right. Good. Yeah.
Would it make sense to break up the O.dot rank and the O.dot shift, like those two different comparisons? Would it make sense to break those up into two different selects and then select like one from the other?
Would it make sense to break those up and into two separate select statements?
Or would that...
That's a great observation. Hold on to that thought. All right, and then projection. What do we got? First name, last name. All right, what's my working set size at each step? Here, how many tuples do I need to process one tuple from officers? 1. Here, 1. Here, 1. Okay, so this is a really nice low memory query. What about time? How much time do I need to put? O of n. So every single tuple in officers, I have to read it in and I have to filter out every single one of those tuples, one at a time. That is a lot of work. That's a lot of reading, and worst off, that's a lot of IOs. And IO operations, today's mantra is, come on, 1, 2, 3. Good, okay. All right, query evaluation. So if I was to evaluate these queries, there's a lot of different ways that I could express any kind of query. One way I could potentially rewrite this would be, in fact, to split up the two selection predicates, and we'll see some examples of that. And different types, different expressions of this query have different properties. Excuse me, I can't talk today. Different queries, different relational algebra expressions can be, the amount of time it takes to evaluate each of them is going to be slightly different. So today we're going to look at one particular way of evaluating these queries that allows us to take advantage of more than just rewriting the query, but that actually allows us to take advantage of some information. Well, I'll get to this in a moment. So let's maybe back up a little and take a look at this selection predicate. So in the absence of any other information that I have about officers, about anything, I'm going to have to take a look at every single one of the rows of officers. What could I do? What could I do to change that, to help me run this specific query faster? Yeah? Okay, so if I were to take officers and sort it entirely by rank, I'd be able to cut, well, presumably if rank ranges from 1 to 5, I'd be able to cut the amount of data that I need to look at in half. And in general, if I organize my data here, that's going to, depending on how I organize it, I can potentially evaluate queries much more efficiently. So one way to do that would be, in fact, to sort everything on rank. Any other suggestions? Yeah?
Well, wouldn't that sorting take time?
Wouldn't that sorting take time? Yeah, exactly. So what I'm getting at here is, so there's, when the data first arrives, sometimes you can't do anything better than just scanning through it. But if you have some time to plan, some time to organize, if you know right now that tomorrow you're going to be answering this query 10 different times, or 10 small subtle variants of this query, you can do a little bit of preparation, like studying for an exam. You can do a little bit of preparation the night before and help yourself answer these queries more efficiently. So that's basically what I'm saying. If you don't know anything about how the data is organized, how the data is sorted, then this is the best you can do. But if you have a little more information, if you have a little time to plan, to sort, to organize, or if you just know up ahead of time, officers is already sorted based on rank, then you can take advantage of that information and answer this query more efficiently. Does that address your question?
It does, but you still need to go through the input to see where the practically ends and it goes up higher sorted.
You're completely right. You'll still need to go through not necessarily all of the input, but you'll need to go through a good chunk of the input to figure out where 3 is. Hold on to that thought. We'll get to it in a moment. So to kind of capture this in a really high level, the problem is that anytime you have a selection predicate, anytime you have a selection operator, you're going to have to read through all of the data. And if you can and that's technically correct, but not necessarily efficient. So if you know that the data is already organized, or if you have the ability to spend some time ahead of time to organize the data, you can make it still a little more efficient. And today we're going to talk about different ways that the data can be organized. So at a high level, there's going to be basically 3 general tricks that we can play. So the first is to actually sort the data entirely. The second is kind of a limited form of sorting. we can take the data and we can put it into some buckets. And if we know what's in each bucket, well, that helps us out a whole bunch when we actually need to read it out. Because if we know which bucket we're supposed to be looking in, like for example, the bucket that has all of the officers on ship 1701, then that gives us, that means we only need to look in that one bucket. And the last thing is kind of a supplement to the first two. Sometimes we'll want to organize all of the data, but sometimes it makes sense to organize not just the data, but organize indexes. Show of hands, who knows what a card catalog is? Wow. All right, some historians here. So a card catalog is basically like this big, for those of you who aren't familiar with it, basically this big thing of index cards and that you used to see in libraries that has written every single book in the library and a pointer to where in the library that book is located. Now you do this all by computer. Still called an index, though. So you go and you don't necessarily have to put all of your data in this, you don't necessarily have to organize all of your data in this way, but sometimes it makes sense to organize pointers to the data. All right. So again, kind of sitting at a really, really high level, the two ways that you can sort the data are that you can, well, either sort the data. And the reason that you might want to actually have these kind of organized pointers as well as the basic data itself is that what if we want to be able to look up, to do efficient lookups on both A and B, both of the two attributes? Is there any way that we can take this data already sorted on A and make it efficient to do lookups on B as well? Okay, so one thing I could do is create a copy and sort that copy on B. And another trick that we could also play is to use pointers. So if I know that this list is kind of almost entirely sorted, maybe I can actually keep a list of pointers that allow me to kind of at least pick out where in the file I need to be looking. Now this idea might seem a little weird, but actually it's what's going to help us take advantage of sorted data, not just when we want to sort on two attributes, but when we actually have data sitting on a disk, and it's going to take a long time to read things in. There is one bit of terminology that I want to make sure you all are familiar with, and that's this approach where we take the data and we sort the entire data set. This is typically referred to as a clustered index. And if we're sorting pointers to the data, this is typically referred to as an unclustered index. All right, any questions so far? Yeah?
Where do those pointers exist?
Where do those pointers exist?
Like, where do you store them?
How are you storing them? So in effect, the unclustered index, rather than, so let's say you have 10 attributes in your data. Normally you'd store all 10 attributes on disk in a clustered index. In an unclustered index, you'd basically store two attributes. The thing that you're sorting on, and then essentially another attribute, which is just some reference to where you need to look for the actual data that you're trying to find. Maybe that's a location on a hard disk, a location in a file, maybe it's a location in memory. What you're pointing to depends on the type of where you're storing. Yeah? Say again? Yes, that is a typo. Thank you. Good, you're awake. All right. So going back to this selection operator, let's say that I wanted, let's go through a couple of really quick just mental exercises. So let's say that I wanted to find, let's say I had some data set and I wanted to find every single value of A that was equal to 1. How would I go about sorting my data and then actually, well, say my data was sorted on A. How would I go about looking up values where A is less than A is equal to 1? Okay, so if I wanted to do it fast, I could do a binary search on my data. I start in the middle. If the middle value is greater than 1, I look to the left. If the middle value is less than 1, I look to the right. Repeat the process. Okay, so I find I find all values of 1, and that seems fairly straightforward. How does that change if I need to do a range scan? So if I need to find all values that are less than 1. Yeah. Okay, so I need to do a binary search for either the first or the last one, and then kind of move off from that point. So if I wanted to find all values of A less than 1, I'd find kind of the starting point of my search, and then keep scanning until I hit keep scanning through the file until I hit the last record. All right, here's another question. Let's say my data is sorted on A, and I'd like to answer this query. Find a specific value of A and a specific value of B. How would I go about doing that? Okay, so if my data is sorted only on A, then I can only really improve my performance on half of this query. So I find all of the values where A is 1, and then I have to just manually go through all of those records and find the ones where B is 2. Great. Okay, so this kind of leads me to the idea, or you mentioned it, that you can take a selection operator and split it up into multiple selection operators. So if you have multiple conditions joined by an AND, all of those conditions have to be true. So it's pretty much the same thing if you apply all of those conditions in one go, one big formula, or if you look at each of those in sequence. So you can take this query and effectively rewrite it selection on rank and then selection on shift. And those two, at least from the perspective of the query's correctness, are entirely identical. So we're going to create, in essence, so the index structure that we're going to today look at a couple of different index structures, and the kind of API that all of those index structures are going to give us is either look up a specific value in the index or give us a iterator that scans over all of the records that fall within some range. So everything we're doing is going to be looking for specific values or looking for ranges of values. Okay, so far we have looked at sorting. Now sorting has some interesting properties that we might be able to improve on a little bit. So let's say I have about 4 gigabytes of data. So this is a huge number of pages or blocks of data, but I know it's all sorted. So how many, let's say I'm doing binary search on this, how many I/O operations am I going to need to do? What do I do first in binary search? Find the middle. All right, find the very center of this 2 to the 20th blocks, load that into memory, and check where I am relative to what I'm looking for. All right, 1 I/O. What's next? Do it again. So now I've split my space in half. How many blocks is that? So I have 2 to the 20th to start. What do I have after I split it in half? 2 to the 10, 19, what? So 2 to the 10th divided by 2 to the 1st, 20 minus 1, 19. So I got 2 to the 19th. I do it again. I load another block. So in 20 steps, I'm going to be able to find the block with the specific record that I'm looking for. So in general, if I have n or 2 to the n blocks, how many operations do I need? N. Or if I have n blocks, I need log of n. Now, I know it's customary in theory and complexity analysis to just say log of n. But can you be more precise? Log to the base of what? 2. So I'm going to have to do log base 2 of n. Why? Because I'm, say that again? Yes. So every single time I look for a record, I start off with my whole set of records, and as far as I know, at the very start, the record I'm looking for could be anywhere. And every single time I load one block, I'm effectively splitting my space in half. And this whole process repeats until I actually find the record. So every single time I'm splitting it in half so that I'm kind of searching in an exponentially larger space every single time I do another step. So I can, inverse of exponential is log. I'm basically building a binary tree as I do my search. So can I do better? So what if I could, with one I/O operation, or let me pivot that question a little, how, with one I/O operation, could I reduce that cost from log base 2 to log base k? Where does the 2 occur in this algorithm? Okay, so if I could fragment at every single step with one I/O, if I could fragment my entire space into k chunks, in other words, if I took this from being a binary tree to being a k-array tree, or, well, based on the slide, an n-array tree, then my tree is going to shrink. I'm going to have fewer steps, and I'm going to be able to do more work, more search work with every single I/O operation. So this brings me to the first type, or the first class of indexes that we're going to look at today. And this is a huge family of different index structures. We're going to look at 2 of them in particular, but generally referred to as tree-based indexes, because they kind of build a tree. One general comment I want to bring up, I don't know if this was intentional when they started naming trees and mathematical functions. It probably wasn't. But anytime there's a tree, you're going to see lots of logarithms. So my mnemonic for this is, if there's a tree, there's a log. That was... Can't all be winners. All right. So the idea here is that we're going to basically take a sorted list, and we're going to call these the pages that are storing this sorted list of records leaf pages. Now, in order to help us do n-ary search over these leaf pages, we're going to supplement them with a little bit of organizational metadata that we're going to call non-leaf pages. So every non-leaf page is going to contain not data, but rather a list of keys and a list of pointers. And for each, using P sub P0, P1, P2 for the pointers, K1, K2, K3, a lot for the keys. So if we're looking for a specific key, we can find that key in this index, and I'll explain that in a little more detail in a moment. But loosely, we're going to find the key in the index page, and the location of that key is going to tell us which pointer we need to follow in order to find the data that we're looking for. So again, if you have, in order to create one of these index structured access method trees, which is basically the simplest type of tree index, you start off with these leaf pages that basically contain all of your data, and we're going to kind of build this organizational metadata on top of it in order to help us do an n-ary search rather than a binary search. Now, in order to do lookups on one of these things, we basically start with the root node, start at the very top of the tree, and we have this list of keys in every single node. We're going to find the two keys in that list that the thing that we're looking for, that surround the thing that we're looking for. We're going to find the one key that's bigger and the one key that's immediately smaller. And from that node, that's going to give us the pointer that we need to follow. We can also use this to do range queries, because all of the data in these leaf pages is basically going to be stored in it's just one sequence of leaf pages. So the tree structure is kind of built on top of it. All right. All right, so any questions on this so far? So how many computations do we need to go and find a particular record? Not IOs, how many computations do we need? Or comparisons, that's a better way of putting it. Log K. So why do you say that? Or, the depth of the tree. Okay, so I'm going to have to do log K IOs, because this tree, every one of those little rectangles is one page. I'm going to start at the root. I'm going to go down. I'm going to find the next page. I'm going to find the next page, and finally, I'm going to eventually get to the leaves. How many operations do I need to, how many computations or comparison, excuse me, how many comparisons do I need to do at the root, back up a little. So how would I find which pointer I need to follow when I'm looking at one of these pages? Okay.
This value is bigger than or less than this value, so you know which tree.
Okay. So the pointers kind of point down through the tree. P0 in this case basically is the pointer I'd follow for everything less than K, every key less than K1. P1 is the pointer I'd follow for everything between K1 and K2. Pointer 2 is between K2 and K3. Pointer 3 is between K3 and K4, and so forth. So in order to actually figure out which pointer I need to follow, I'd actually need to do a whole bunch of comparisons on K1, K2, K3, K4, so forth. Can I do better than that? Can I do better than just a sequential scan through the through? So what did I do? What was the trick to finding? I had a big sorted list of data. What was the trick to finding the one record I wanted? Binary search. Okay, so I can do binary search within the page. And I just want to emphasize this point because this is the one case where this is one case where the idea doesn't entirely translate to higher levels of the memory stack or the memory hierarchy. You still need to do a log-based. The tree is still in effect a binary tree. As you're searching, you still need to do a binary search at each node. At each page. But the advantage is that you load these pages in bulk. So you only need to do one I/O for a much smaller number of. Back up. I/Os are slow. Comparisons are typically fast. So even though you're still doing a binary number, a log base 2 number of comparisons on this, you're getting much better performance because you do fewer I/Os. You do log base K I/Os. All right. So we've discussed how you build an ISAM index to start. We've discussed how you read stuff out of an ISAM index. Does anyone see a problem with? Does anyone see Is anyone getting kind of a weird sense that I might not be telling you everything? This might not be the best index structure. What are the weaknesses of this? Would be another way of putting it. If I say
If you want to get all the data at once and just scan through them all, it wouldn't be as good as.
okay, so if I want to get all of the data out of the index, if I want to do a full scan over the index, would it be as good as just having a sorted file? Well, that depends on how the leaf pages are organized. So if I'm a little bit clever about how I create the leaf pages, I can put them all in one contiguous region on disk. So I mean, as far as I'm concerned, that page has all of the records that are immediately after that page. That page has all of the records that are immediately after that page. So if I just put them in one contiguous block of pages, I'm not actually losing anything over a sorted list because I can still do a scan, and I now have this kind of extra index information sitting on top. Maybe I'll put this in another way. If I have all of my data in a sorted list, that's good for some things, that's not necessarily so good for others. What are some pros and cons? Insertion. How do I do insertion into this? It's weird because I got all my data in these leaf pages, and that's all a big sorted list. So yeah.
This insertion might be from, is it like another type of tree? You add the node, start at the top, and go to where you find an empty leaf branch.
Mhm.
And then when you find a branch of added new seed and stuff, it causes the.
Okay, so I could start at the very top. I could kind of go down all the way and find a node. And then I can kind of pray that there's a little bit of extra space left in that leaf node. And if there is, okay, great, I can put my data in there. What happens if I don't have space?
Then you create a new non-leaf node and make a new branch.
Then I could potentially create a new non-leaf node and create a branch from there. That's an interesting idea. Should have invented a time machine and go back and tell the folks who were doing these ISAM trees what to do. So yes, that is a really good idea. Is actually not the idea that typically arises in an ISAM index. So what often happens, or what typically happens, is that these leaf pages end up getting overflow pages. So in addition to the regular list of contiguous, oh, actually, let me back up. So there is one reason that you wouldn't want to do that, and that's this argument that I was making a little earlier, that all of your data is in one contiguous sequence of pages. So if I start off with all of my leaf pages in sorted or in just one long sorted list of records, then if I was to turn one of those leaf pages into a non-leaf page, index page, then I'd lose my nice contiguous list of I'd lose my nice contiguous list. So what will typically happen in an ISAM index is that you'll have overflow pages. So certain pages might say, oh, by the way, in addition to the stuff that you're seeing in this big contiguous list, also here's another page of data that you should look at. This is kind of a weird trade-off because sometimes you do want that contiguous list. This only really works if you don't have many overflow pages. So we're still, this is still a little bit awkward. Right, so a little bit of a simple example here. So I've got my big sorted list, 10, 15, 20, 27, 33, 37, 40, 46, 51, 55, 63, 97. And my non-leaf pages basically tell me where I can look in this tree. So since I have 3 pointers at every single non-leaf node, what is the expected depth of this tree? Log base 3, n, yeah. So if I want to do an insertion, let's say I want to insert a, let's say I wanted to insert 23. What would I do?
Create an overflow page on page 2027, move 27 down, insert 23, go to the next one.
Okay, so I'd have to create an overflow page on that second leaf page. How would I know that? That's correct, but how would I actually know that that's what I need to do?
You have to traverse the tree.
To traverse the tree. So we start with 40. 23 is definitely less than 40. It means I take the leftmost pointer. Then 23 falls between 20 and 33. So we follow the middle pointer there. And we do our insertion. Let's say that we wanted to do insertion, a whole bunch more insertions. Let's insert 40, a whole bunch more stuff. And now let's say that we wanted to start deleting things from this tree. So I got a 97 in that last page at the end. Let's say I wanted to delete that. Well, basically overwrite the chunk of data that overwrites the relevant portion of that page, like we talked about last class. And let's say I also wanted to delete that 42 I just inserted. Could I do anything at that point that would make my life easier? The page suddenly becomes empty, I can get rid of it just as easily. All right. Getting a little bit low on time. So an ISAM index is basically kind of the lowest hanging fruit when it comes to trees. It's really simple to build, really simple to access, but it is not very efficient when it comes to updating data. So what happened next, or one of the kind of follow-ups to ISAM indexes, was this thing called a B+ tree. B+ tree is going to come up all over the place, not just in databases. And they differ in two really simple ways. So first off, the data pages aren't stored sequentially. So they're organized into a linked list. They're still sorted, but now they're in a linked list. And the second difference is that is the way that the tree structure looks like. So the tree structure, for the most part, works pretty much exactly like an ISAM index, in that if you wanted to find 5, you take the leftmost pointer. If you wanted to find 15, well, 15 is between 13 and 17. You take the second pointer. And if you wanted to find any records that were bigger than 24, you'd follow the fourth pointer and then kind of scan further through the file. The difference is that in a B+ tree, we're allowed to, and in fact we want to have open slots in both the leaf pages and the non-leaf pages. We want to keep space open so that we can insert new records, both in new records into the leaf pages and new keys into the inner nodes, the non-leaf nodes. But this is going to turn out to be a little bit of a balancing act, because if the leaf pages are not full enough, then we're basically back to a much lower degree of fan-out, which in turn is going to create a much deeper tree than we actually need. So a B+ tree basically operates using a very simple invariant. Every node has to be at least half full. So we're going to create we're going to talk about ways of creating new nodes and destroying nodes that will enforce this invariant, essentially allowing us to keep each of the nodes at least 50% full. All right, before I get into that, let's let's take a quick 5-minute break, and we'll resume at. All right. So once again, a B tree is going to have the same general structure as an ISAM index, but the two differences are, first off, the leaf nodes aren't contiguous, and the second difference is that we're going to keep a little bit of open space in each of the inner nodes and each of the leaf nodes. So whenever a node gets full, we're going to split it and whenever a node becomes under full, we're going to merge two nodes together. And all of this is basically going to keep one specific invariant, which is that all nodes must always be at least 50% full. So in the running example that I'm going to show you, the inner nodes are going to have 4 values and 5 pointers, which means we need how many? Just testing to see if you're awake. How many keys? So if I have 4 values and 5 pointers, how many do I need to maintain my invariant? At least 2, thank you. Some people are awake. Let's try that again. 1, 2, 3.
2.
Good, okay. All right. So I'm going to have 4 fields in each of my leaf nodes, in each of my data nodes, and I'm going to be able to, I'm going to want to make sure that everything has at least 2 things full. So let's say that I want to do an insertion of an 8. So 8 is less than 13. I'm going to follow my left pointer, and that's going to bring me to this data page here, which currently contains 2, 3, 5, and 7. So 2, 3, 5, and 7, what I need to do is insert my 8 into that. All right, just did my insertion, at least conceptually. Anyone see a problem? That's 5. This is overfull. So I'm going to take the middle record in there, and I'm going to use that to split the data node. So in this case, 5 is the middle attribute, and I'm basically going to create 2 new leaf pages, one that holds 2 and 3, and the one that holds 5, 7, and 8. Is my invariant satisfied? Yes. Is it guaranteed to be satisfied? So in general, when will I do this? When it's too full. So I have n plus, let's say 1. If I'm doing one insertion at a time, I have n plus 1 records. So what's my invariant again? 2, or half full. So if I have 4 or 5 records, and I split that in half, am I always guaranteed to get more than 2? No. Okay, 5 divided by 2. I know we're all computer scientists. We use calculators, right? I see some people with laptops open. 5 divided by 2 is around 2.5. So I'm guaranteed that both of these are going to have at least, I'm going to have at least enough data to put in 2 records into one and 3 records into the other. And in general, if I have n records that will fit into a leaf page, then n plus 1 records is when I split, and n plus 1 over 2 is always going to be at least half of n. All right, so now we've created these 2 new data pages. Now we have a little bit of a problem because we need to take, we need to create, we need to insert that new leaf page into the index structure. So I have my keys there, and I want to basically take that 5, so that 5 is a good partition point, and I want to copy that into the non-leaf node that is sitting above the data page that I just split. I'm going to do that. I'm going to take my 5. I'm going to create a new entry. Problem? See some people nodding. Come on. Yes. Okay. Thank you. All right. I need to do exactly the same thing now. So I have 5 records. I want to split that in half. So I'm going to take the middle record in there, and I'm going to move that into another node. Now at the moment, I only have one index node in my tree, so I need to essentially split the root. So I'm going to put 2 records into my left-hand side, 2 records into my right-hand side. Anyone see a slight difference between what happened here and what happened with the data nodes?
17, you only have one values in the phone instead.
Exactly. So in the previous case, I actually had to keep the 5 in my leaf nodes. Here, I was able to move the 17. Any idea why I'm allowed to do that?
Magic?
Magic. Yeah, the magic of animations. So how many pointers are there in a non-leaf node? So there's the one left of 5, the one to the right of 5, the one to the right of the 13, the one to the right of the spot there, the small little blocks. How many pointers do I have? 5. Why do I need 5 when I have 4 keys? Exactly. So I have a whole bunch of records that are less than all of the keys in the block, and I have a whole bunch of records that are bigger than all of the keys in the block. So I'm going to need exactly one more pointer than I have keys. So I have one pointer for everything less than 5, one for everything 5 to 13, one for everything 13 to whatever falls into the next slot, and one pointer for everything between that slot, next slot, and then one pointer for everything bigger than the last slot. So in this case, I basically have one pointer that represents everything bigger than 13. But does that actually have all of the data? If I follow the pointer to the right of the 13, does that lead me to everything that is bigger than 13? All of the records that are bigger than 13? No. Why? Right, so that root node gives me an upper bound. So the 17, in effect, what that pointer to the right of the 13 means right now is not everything bigger than 13, it's everything between 13 and 17, because I already have that constraint. If I'm visiting that left-hand side node, I have already asserted to myself that the only things I'm looking for are less than 17. Yeah?
So by default, if it's equal, it's on the right?
By default, if it's equal, it will always be on the right. That it's always going to be either on the right or the left. Which of them doesn't matter as long as you establish a convention and stick with it. I tend to use it's always going to be on the right, but
On the case that, let's have the lower node so as to have the spaces, but the top node is full and the greater than node is all full. And let's say a greater than node adds to the upper bound, there's 5. But in any case, it go down to the lesser node and add to that, or just create a new node.
not sure I follow. So if
Basically, if it's greater than 17, that all fills up, and if there's more stuff greater than 17 up there, and that's all filled up, and there's a 5th node on the 17 row, and there's still 2 empty spaces in the less than 17 row, will it, in any case, add to that, or?
I see. So will there ever be a case where a higher node in the tree fills up before a lower node in the tree?
Yeah.
Okay. Hold on to that question, because I think I have an example up here that will illustrate the intuition behind the answer that I'm going to give. So one thing I just want to note, the 50% occupancy guarantee, the invariant, is the one node that is exempt from that is the root node. We might not, and as you can see in this case, it might not always be possible to fill that up. But okay, so let me go through a really quick example of doing some operations. Let's say that I wanted to delete 19 and then delete 20. So I delete 19, I delete 20, And now I'm left with one record in that data node. So there's a couple of options open to me at this point. I could possibly just eliminate that data node outright, but at least in this case, as it turns out, the node immediately to the right of it has 3 values in it. So what I could potentially do at this point as a slight optimization is actually move 24 from the leaf page on the right to the leaf page on the left. Of course, if I do this, I also need to update my keys accordingly. Let's say I wanted to delete 24 at this point. Well, now I only have one record. My invariant isn't satisfied. So I need to merge 2 nodes together, 2 leaf nodes together. And when I merge 2 leaf nodes together, the parent also kind of slides over. And now the invariant isn't satisfied on the left-hand, on that node on, excuse me. Now once I do that, the invariant is no longer satisfied for that leaf node, so I need to merge it together with the node to its left. Okay, so what I'm essentially trying to get at here is, so to answer your question, the merges and splits always propagate from the bottom up. So if I have, the only time I'll ever split a node is if all of its or if one of its children has already been split.
Okay.
So to answer your question, no, you'll never have a case where the root needs to split, but one of its children doesn't. Any other questions? Yeah.
Could you go back when the root only have 17, and then you go back as if you use 19 and then 20 in their page?
Mm-hmm.
So now only the bottom leaf is 20, and then you merge with 24, 27, 29. What about right there? I'm going to insert 90 again. Oh, we go to the root.
So
with
I do
17.
that.
Yeah.
So I delete the 19, then I insert 19 again.
Yeah, so I'm going to 17, go to the root, or will you go to the bottom again?
So if I want, so I'm skipping a few steps here. If I wanted to delete the 19, I'd start at the root. 19 is greater than 17, I'd go to the next node. 19 is less than 24, and that points me to the node where 19 exists.
So the root is non-null, still will go bottom, fill in the bottom, then goes up.
Yeah, so if I wanted to insert 19 at this point, I'd once again start at the 17 and say 19 is greater than 17, 19 is less than 24, that leads me to that node. That node now has space, I put the 19 in there.
So as a convention, wouldn't it be better to, like, once you delete 20, to move 22 into the block to the right, so that it uses up the rest of that space instead of having 2 that are 50% full?
Would it make sense to try and compact nodes as aggressively as possible? Is that a reasonable way of?
Yeah, so I know it's not sufficient for type insertions after, but it would kind of cut down on the likelihood that at any point your tree is only or your pages are only 50% full.
Yeah. So this. Okay. So there's 2 answers. Okay. So I told you guys that there was an answer I would give over and over and over again. Anyone remember? It depends. Yeah. So what are the advantages? What do I get by clustering by compacting the tree as aggressively as possible?
More space efficiency.
More space efficiency. Anything else?
You're preparing more deletes.
Okay, so more space efficiency, more efficient deletions because I'm compacting things more aggressively. Also, by compacting things more aggressively, I'll actually end up shrinking the tree a little bit, so I'll actually have better performance on reads. What am I giving up for that?
Insertions.
insertions. So by having open space, that makes my insertions faster. So the short version, it depends. Do you want to do more reads? Do you want to do more deletes? Or do you want to do more insertions? So does that address your question?
Yeah, I just thought it was like, as a convention, it's counterintuitive to do that first.
To do,
To move one to a page that you could delete.
oh, okay.
Just
Would it
for an example.
would it make okay?
It just seemed like a more like standard.
Oh, I see. Would it? It's kind of. Why would it make sense to move one record from 24 to 22 rather than 22 to 24? One point I'd like to illustrate. I'm keeping the sizes here small just so stuff fits on the slide. But typically, what we'd be looking at here is not just 4 records. We'd be looking at 400 records, and half of that is 200. So it's a difference between moving one record from something with 201 records to something with now 199 records versus moving 199 records over into the other slot. Does that address your concern? Okay. Yeah.
By maintaining that 50% mark variance, other than that you kind of save space a little bit, is there any other advantage?
Is there any other advantage to maintaining the 50% invariant? So the one big thing, as you pointed out, is space. But space actually has another advantage to it. The fewer index pages we're using, the fewer reads we need. So one way to put this, the depth of the tree is never going to be worse than log k over 2. We want k to be as big as possible. And k, in this case, is limited by the size of the page. So ideally, for efficient lookups, we want k to be as big as possible. We want that logarithmic base to be as big as possible. And by ensuring that we keep it at 50% full all the time, we're never going to have a tree that's deeper than log k over 2. Does that?
Can you increase the variant to save more space and change the less rate operation? Or where did that come from?
Where did the 50% come from? Can you increase it to save more space? So the 50% invariant comes from the fact that if you split 2 pages, you end up with half as much data. So this is the easiest invariant to maintain. There's more complex data structures. I'm not going to talk about red-black trees. But the 50% is basically because 50% is what you can do efficiently. Yeah.
How does choosing your K? Like,
How do,
algorithm or like,
how do you choose K?
Yeah.
So this is basically a limiting factor of the pages. So 1 IO gets you 1 page of data. That's depending on your operating system and environment, 1K, 2K, 4K, a meg if you're using HDFS, but your page size is fixed. So K is however many keys and pointers will fit into 1 page worth of data. Is that? All right. So that is all I think we have time for today. We'll get back into hash-based indexes next class. See everyone then. Hopefully less snow.